our solution is therefore the form Q of t equals A times the cosine of omega t, omega being 9 times 10 to the 4th radians per second, plus theta naught. The reference circle picture is simple enough. I've kind of sketched it here. We start with some theta naught, and our reference point moves around the circle with angular frequency omega, 9 times 10 to the 4th radians per second. Now that, as I said previously, but just to write it out, implies that the frequency is 9 times 10 to the 4th radians per second divided by the 2 pi radians it takes to complete a cycle, 2 pi radians per cycle, and you do the algebra of the units, you come up with cycles per second, or hertz. So 15,000 hertz, 15,000 cycles per second, natural frequency of this oscillator. The current, of course, we could get by taking the derivative of the charge function, and we just get the chain rule gives us our omega out in front here, and we get a sign and we get a negative, so that we have the same frequency for the current. But one thing I'll note and didn't note in class, and I'll have to come back to this, but note that the sign is 90 degrees out of the negative sign is 90 degrees out of phase with the cosine. The current is out of phase with the charge. The charge being the voltage on the capacitor. So you have this phase difference between voltages and charges that we'll talk more about in the upcoming chapters, something you want to be aware of at this point. Okay, and if you take, if you throw the switch on that circuit that I no longer have in front of us, but if you throw the switch on that circuit at t equals 0, then your charge at 0 is going to be what? The 4 microfarads multiplied by the 16 volts. Okay, and that's going to give you 64 microcoulombs of charge, and what I have equals 64 microcoulombs equals 64 microcoulombs. No good explanation for that. And this is assuming, of course, that theta naught equals 0. So that, and I know what I did there. Let me correct it. Of course, this is equal to 64 microcoulombs is equal to 64 microcoulombs. But that's equal to A, your amplitude of your charge function. And if we assume theta naught is equal to 0. Okay, now we're going to go a little bit further into this. We want to understand what's going on with this circuit. So the switch is closed, and we've got this fully charged capacitor. So we have a large electric field in the capacitor. So we have energy in that electric field. The energy in a capacitor is Q squared over 2C. That could be regarded as the energy within the electric field that occupies the volume between the capacitor plates. And when we first throw the switch at time 0, we have no current. So we have no energy here. All the energy is in our capacitor. Now, the capacitor, of course, having energy, can discharge its, well, it can discharge, it can transfer its charge from one plate to the other, or even in both directions, depending on what's conducting it here. So what's going to happen is this capacitor is going to eventually discharge. And of course you have the current through the inductor kind of chasing the decreasing charge on the capacitor. As we said, that's what gives you the trigonometric, the sine or the cosine nature of the result. But it's going to discharge, so you're going to come to the point where you have no charge on the capacitor, so you have E equals 0, and of course there's no energy in the capacitor. But now you have a maximum current, and your maximum current is going to give you a maximum magnetic field. Okay, so the magnetic field is drawn here. The magnetic field has this shape through the inductor, and the energy in that magnetic field is 1/2 Li squared, as we've seen previously. Now ignore this stuff in orange here for the second. We'll come back and talk about that. Okay, now what's going to happen? You've got a current. Okay, well, the current is in the process of transferring charge. It's just that at this point, the charge has hit zero. But the charge is going to continue, say, decreasing. Let's say you have a maximum positive charge here. Your charge gets to zero. This inductor is pushing back in the direction opposite the push of the capacitor, the initial push of the capacitor. So it's going to drive the capacitor to lower charge, to negative charges. And that's going to continue until the inductor stops pushing charge around, which is going to happen when its current is zero again. And at that point, you're going to have, again, a maximum magnitude of the electric field, but it's going to be in the direction opposite the direction you had here. And yeah, just to be consistent, I had 4 little arrows here. Let's draw a 4th arrow, even though they're not going to be particularly well spaced, just to indicate we have the same amount of charge here as we had here, just in the opposite direction. Now this assumes no dissipation, so no energy loss in the circuit, which means basically no resistance in the circuit. There is always some resistance, so you're going to end up with a little less energy here than you had here. But the energy is then back to Q squared over 2C. And now we can understand that the charge, well, the electric field here is conservative, and the energy of the capacitor comes about just by transferring charges, and as a result, this is everything that happens on this capacitor is conservative in nature. Okay, the electric field is created by the charges on the capacitor is conservative throughout. So that this Q squared over 2C is a potential energy. The capacitor has potential energy. It had potential energy Q squared over 2C here. Okay, transferred that energy to the energy of the inductor here. Now, by analogy with a harmonic oscillator, where you have, let's say, a pendulum, you have maximum potential energy here and maximum potential energy out here, and zero potential energy at the equilibrium point where you have maximum kinetic energy. Your potential energy starts out here. That's a potential energy, and it might be okay to notate it here. That potential energy transfers to the 1/2 Li squared. Well, that's analogous to a kinetic energy, and the kinetic energy isn't conservative or non-conservative. It just responds to changes in the potential energy. The analogy being that current is somehow analogous to velocity, and the inductance is analogous to mass. Now we'll go on a little bit further with that analogy, but for right now we can understand this as an analogy with the energy state of a harmonic oscillator. And I'll also comment, your book makes a big deal of this, and it is a big deal. One thing that engineers do is model mechanical oscillatory systems with electrical oscillatory systems. You set up an electrical oscillatory system to be a perfect analog to what you think is going to happen in a mechanical system. You take the readings, which are much easier with an electrical circuit than they are with most mechanical devices, most mechanical systems, and then you just translate your results over to the mechanical system. So it's a very powerful technique and a very powerful analogy.